Ever wondered how a machine with no wings can lift straight off the ground, hover in midair, fly backwards, sideways, and even spin on the spot like it's rewriting the rules of aviation? Today on Knowledge Hub, we're breaking down the incredible engineering that lets helicopters do what no other aircraft can. At the heart of every helicopter is the main rotor system, essentially a set of spinning wings. As each blade sweeps through the air, it creates lift using airfoil physics, but unlike airplanes where airflow is steady, rotor blades constantly move through changing aerodynamic conditions. One blade is always advancing into the airflow while the opposite blade retreats, creating asymmetric lift. Engineers counter this using blade flapping hinges and cyclic pitch control, which dynamically adjust blade angle and position during every rotation. The advancing blade automatically flaps up, reducing lift, while the retreating blade flaps down, increasing lift, a self-balancing mechanism that keeps the rotor disc stable. This entire operation is coordinated by one of the most fascinating mechanisms in aviation, the swash plate assembly. The stationary swash plate tilts according to pilot input, and the rotating swash plate follows it, transmitting those tilt changes into pitch adjustments for each blade multiple times per second. This allows the helicopter to tilt the rotor disc to move forward, slide sideways, or crab into the wind. Meanwhile, the collective pitch lever changes the angle of all blades equally, increasing or reducing total rotor thrust. Pulling up on the collective increases lift, but it also increases drag on the blades, so the engine's governor system automatically boosts power to maintain constant rotor RPM, one of the most critical parameters in helicopter flight. Inside the hub, lead lag dampers prevent blades from swinging too far forward or backward from rotational momentum, reducing dangerous vibrations. And because the rotor is a giant spinning gyroscope, any input applied doesn't take effect instantly. Due to gyroscopic precession, the change happens roughly 90 degrees later in rotation, something the swash plate and control linkages are specifically designed to handle. But lift alone doesn't solve everything. When the main rotor spins, it tries to twist the helicopter body in the opposite direction to stop the fuselage from spinning uncontrollably. Most helicopters use a tail rotor, a sideways thrusting propeller that counters torque. Pilots control it using anti-torque pedals, allowing the helicopter to rotate left or right with precision. Modern designs upgrade this with fenestron enclosed fans for quieter, safer operation, or NOTAR systems that use high-pressure air, and the Conde effect to provide yaw control with no exposed rotor at all. Beneath the aircraft, a powerful turboshaft engine drives a transmission that reduces extremely high turbine speeds into the correct rotor RPM, while also powering hydraulics, avionics, and cooling systems to keep the helicopter stable in turbulent air. Many models rely on stability augmentation systems, electronic gyros, and vibration absorbers that constantly smooth out the flight experience. And even in the worst-case scenario, total engine failure, helicopters can still land safely through auto rotation, where air rushing upward through the rotor turns the blades like a windmill, producing enough lift and control to glide down and touch down softly. From rescue missions in confined spaces to military operations and medical evacuations, helicopters work by harnessing complex aerodynamics, rapid mechanical adjustments, and finely balanced forces that come together to create the miracle of full-directional flight. If you're enjoying these deep dives into the machines that shape our world, make sure you hit the subscribe button so you never miss a new video from Knowledge Hub. And as always, stay curious.